Bernardini. I'm the chair of this session. So we are ready to start with the first talk, which is towards automating crime prevention through environment design analysis to predict burglary. And Simon Parkinson is going to give this talk.
Okay, hi everyone. So my name is Simon Parkinson from the University of Huddersfield. Okay, so I'm here to talk about this this project we've been working on with our local police force in the UK, West Yorkshire Police, and also Manchester Met Police. So I'll explain a little bit about what's going on, but this is kind of early work leading to like a larger project in the UK. One of the key themes that's going on within policing is this whole digital policing area. And a large portion of that is around automation and trying to improve crime prevention, really. So let's look at what it is. So crime prevention through environmental design. Okay, so this is actually quite a straightforward area conceptually. It's about making sure that when somebody designs or builds a new housing area, they take adequate prevention to minimize the risk of crime occurring. Okay, so this is always based on historical context, really. But just some examples there is like this one up on the top there. So this is an example where there's poor access control, really, which allows people to move freely in and out of the housing estate. This example in the middle, probably quite a familiar one, really, where you've got these high fenced areas where people can easily move undetected. And then the final one, which is a very typical thing in the UK, where people kind of like to have very high hedges around the property to increase privacy. But when you increase privacy, you're actually increasing the potential of crime because people can't really see that it's happening. Yeah, so it really is easy to avoid detection. So although this might appeal nice to somebody, it actually appeals even nicer to the criminal, if you like. So the CPTED, so crime prevention through environmental design, is the area of studying the potentials really before it's actually built. Because obviously when the environment's built, you have limited chance to actually change it, right? So it's a before thing to do. So there's kind of 5 areas that exist within it, and these are quite straightforward and high level as well. So the first one is around surveillance. So it's not surveillance in CCTV, it's around natural surveillance. So when the architects design these plans, it's around making sure that one property has windows looking out onto certain areas that perhaps are I don't know, easy to hide within. Not so that person has the obligation to look, but just so there's some natural surveillance. So it's kind of a two-way battle, if you like. The person in the house is able to survey, but the person who might be wanting to commit crime knows that there's a potential for someone to see them. So that in itself tries to reduce it. Physical security, okay, so this one's around fences, window locks, all these kind of areas. Movement control, this one's around predicting where people walk and trying to make sure they don't walk somewhere that could lead them to crime opportunities. So for example, if you had a housing development, you wouldn't want a public footpath to go along the back of everybody's house where everybody's probably enjoying recreational activities and the defence is quite low, right? They're probably in and out of the house, the back door's always open. So you have to consider these kind of things. Defensible space is a big one, and you probably have this problem a lot in the US, really. This is where properties like to have an area around them, which is, they call it defensible, although there's no actual defence taking place there. It's an area that belongs to the property and often prevents movement control. And when you have big housing developments, high-rise apartments, for example, you don't necessarily have this around the bottom. Whereas if you have a small house, the footprint is often bigger than the house and you have the area around it, and this is so-called defensible space. And then the final one is management and maintenance. This really comes down to trying to predict what people might do. So if someone has a garden and that garden's obviously going to have a lot of trees in there, you can probably predict that they're probably not going to maintain them and it's going to become quite overgrown and easy to hide. Okay, so that's enough about the background there. So now a little bit about why we've been looking at this. So in the UK, well, England and Wales, I'm not too sure what Scotland and Ireland are doing really, but in England and Wales we have 43 police forces, and each one of those is responsible to review every proposed housing development. So when the architect develops, they have to send it to the police. The police have to look at it and give their interpretation of it. Okay, and then they pass it back to the architect who then really would design and change it. There are some challenges with this, as you might expect. Resources are obviously a big problem. Throughout the police forces, typically one person is responsible for this, and that one person is also probably serving police officer, so it's a big bottleneck on resource. Consistency is a problem because there's a lack of formal literature around it, really, so people are doing what they think is best based on the local crime in the area, but there's a lack of sharing of information. And then completeness, if somebody rushes it, they're obviously going to miss some important things. And then when it comes to the actual communication between the police and the architect, they use different language, which causes big barriers. So the police approached us really to see if we could consider producing a sort of a prototype for them, and I've got it to show you at the end. In fact, if you came to the demonstration, you'd seen it. A prototype which shows them the potential of using an automated technique rather than using their traditional manual approach. So the first thing we had to do here is we had to try to work out what the police were actually doing. So they were very cooperative in this. So what we did is we gave them a series of site plans. So here's one from York, okay? And we sent them to all the police forces who were cooperating with us and asked them to give us their analysis, right? And send back what they found and also some context around it, you know, why that was important, what they would recommend doing, etc. And we got that back for all of them. So the process is a one-to-one basis, sorry, I should say there. So we just asked them what they like and what they don't like and give the details. In the paper, I have more information about what the actual findings were specifically, but here I'm just on the high level, really. So just to kind of give you some examples of some of the things that they were really, the strong themes that came out, if you like. Now, I know it's a little bit difficult to see on this, probably, on this Google Map image here, but one of them is around, there's a small footpath between this property here, which allows people from a public road here to come onto a private road, and there's no surveillance in the footpath. Now, interestingly, actually, since this housing development was built, if you actually look on this on the map, they've put a wall to stop it, so you can't even move through it anymore because they realised it was a big problem. Another one that comes up often is around actual parking. Obviously, vehicle theft is a great target, really. So, you know, actually making sure that you try to minimise that through having overlooking properties and access controls is important. And that's an area around here. Another one is, you can't see it on the plan here, but these houses on the bottom have a very hidden path at the back of their properties to basically to take out the rubbish, right, from the bins to the road. But it's very hidden and easy for people to move. So that's obviously problematic too. Another one is this collection of properties at the top here, because they're bordering a public road, but they also have a road all the way around them, so they're quite isolated, right? They don't really have a defensible space around them. Somebody can walk all the way around it very easily, and because of its location next to the road, nobody would really be suspicious of somebody walking around there. And then the other ones are this large property on the end here, which is a collection of apartments, really. And it has parking all the way around, but it's so easy to move around there. So there's no access controls, and there's a lack of defensible space. And there's also a lack of natural surveillance on some of the more hidden car parks. And you know, when you have car parking areas that are not overlooked in any way, you often find that they get linked to antisocial behaviour, right? People drive their car there late at night, play music, do recreational activities, which probably aren't in the favour of the residents. So it's a bit of a problem. Okay, I'll just skip this one. So what we did then is we got all this knowledge back from the police forces. Then we put this into a domain model because they wanted us to take that and then relay it back to them pretty much to show them how we could do some automation. So I'm not going to go too much into detail really on the domain model in this presentation. It's in the paper, but the things I want to just highlight really is it's actually quite easy to model what was going on, because obviously when you've got a site plan like this, you've got types of objects, you've got houses, roads, etc. And then you've got the logical connections between them. You know, you've got a house next to a road, or you've got a public road next to a private road with a path between them. And these kind of relationships are what allow you to then work out what the potential is. We also modeled the reduction characteristics. So these are like crime reduction properties, if you like. So one of them is a building overlooking a path, perhaps. We take a very building-centric view here because the thing that the police are really interested in is what the crime potential of the building is. There's obviously other ways of looking at this, but for now we're just focusing on the building. Then we have a look at the crime aspect. So we have a look at what the attraction might be to a property. Does it have poor surveillance? Does it have easy access? And then we have crime methods. What are the ways of actually executing an attack, if you like, against it. And then when it comes to some numerics we've got in here, we've got a crime method score, and I'll explain this on the next slide actually, how this plays out. So one thing we learned from the action knowledge that we got back from the experts, if you like, because the police guys doing the analysis, it is very much a deliberation task they're doing, right? They're looking at it and they're trying to work out if that's a potential, etc. So we realised that, okay, there's kind of like a zero cost assessment one, which is just, okay, I looked at that property and I can't find anything wrong with it. The next level is the crime opportunity, so that's where you find that there's a potential in the environment for a crime to happen. So an example there is lack of surveillance or easy access. And then we have the crime method. So the crime method is actually the execution of a crime, theft, vehicle theft, etc. Now what we do in the domain, because we want to make it so that it's modelling it in a realistic fashion, we take the crime statistics of the UK and we use them in the methods. So, for example, there's a lot of, the data is readily available actually that say, okay, X amount of properties were burgled last year. You can then take this into and kind of come up with and that's on a regional basis. You can take that and kind of work out what the percentage opportunity is that a property would be burgled. And that's kind of what happened. So we took one of the same plans same architect plan that we gave to them to get the information, and we encoded that alongside our domain model and alongside the numerics. So one thing within this specific one here, just for example, is there's 95 properties, 5 private roads, 2 public roads, etc. Now you might think, why there's so many roads? Well, that's because in the UK, for this plan specifically, in the middle of the housing development, it's actually separated into separate roads, which is a bit strange, but okay, we modelled it in this way. But when I actually show you the application we gave back to them, we actually merged them all into one because it makes no difference. So just some example of the numerics that went in there, for example. So house theft or vehicle theft, you can see that we just take the percentage opportunity and use them. And then it makes it, when we actually get the plan output to give back to them, we can give them that value back, and they can infer on that whether they think it's important or not. And it also allows us to do the maximization, right, when we're doing the planning. So just an example output plan. I won't go too much into detail of this because I chopped and changed it just for the purpose of easy demonstration, really. When we actually did the planning of this, there wasn't really anything found that we didn't get back from the police. So that's kind of reassuring for them, I guess, that we didn't beat them. But we could show that we found the things that they found, right? And that's kind of obvious, because we encoded their knowledge, really. So if we didn't find what they found, we'd have been doing something really wrong, or the encoding would have been wrong. So I won't go into detail on what these are, other than showing you that you can see it's around identifying that there's buildings next to paths, and then there's opportunities for crime, and then there's the execution. So, for example, like down here, you've got the lack of defensible space, which leads to the theft, if you like. So then the next thing they asked us to do was to basically demonstrate a case study to them on a new development, one in Manchester. So it's one on the side here. This one was slightly smaller, only 42 buildings. They wanted us to take this and then give them the output, right? So this one's a little bit different in that we didn't learn based on this data, so it's new. And there were 3 things that really came out of this. Similar sort of output to the one before, where it's around having public paths next to properties with a lack of defensible space, and then around having these areas down here where you've got a lot of access from the road, easy for people to migrate in. Since actually this obviously was approved and was built, and you will notice if you ever look, if you look in the paper, you'll see actually that there are bollards installed, right, to stop people coming through with certain types of vehicles, etc. And then another one is around a path connecting these properties here, which is obviously very easy to hide within. So that was kind of successful, and they liked that. But one thing that we had to do, because we were obviously dealing with the police, they didn't really want to see some conceptual stuff. They wanted to see something in action. So we created a little application, and this is what we were demonstrating the other day. And the way this works, it's quite simple actually. Although this is not how it would work in the future. This is just a prototype. The police person or the architect can upload the site plan, and then they can mark it up. Now, what's going on here is that we overlay a grid, and then we ask them just to colour the squares. Is there a property there? Is there a road there? The reason we do that is because we need to extract information of where the houses are and the relationship between them. Ideally, we'd automatically do this from the image or from the architect's software. But for where we are at the moment, this is completely acceptable, considering they do it actually on paper. They don't even review this on a computer. Actually, the police print them out and write on them. So so we're already trying to help them in some ways. And what we do then is it's easy to extract the objects and the links between them, and then this allows us really just to create the problem instance and do the planning and get the output. And then if you came to the demonstration, that showed that when on the output, if you actually select the action, if you like, or to say that there's a lack of surveillance or the likelihood of theft. When they select it, it highlights that property. This one's obviously a small site, and the resolution of the grid is quite large, so it's you can see there's not much detail here, but it works. In terms of the actual planning behind it, this one's just using LPG, and the reason for that was just because it's easy integration with this kind of thing. There's no reason why we wouldn't consider using another planner, and with the demonstration, we just gave it an upper bound, so we just said, okay, find the top 10 plans in 30 seconds, and that's good enough for this. Obviously, it's not guaranteed to be optimal, and there's work to be done there, and that's where we're going in the future, really. And one of the areas that we're really looking at in the future, actually, is whether, as well as just discovering what could happen there, can we actually suggest changes to the environment? Can we actually suggest that they might want to reorientate things, perhaps, in the plan automatically? So really, we're trying to take the technology away from the police and put it with the architect, really, so it's a bit more seamless. So in summary, we've demonstrated that we've got this approach where we learn from the expert. We got the knowledge, we put it into our domain model, produce a little tool to show them it working, and they seem very happy with it, and it does work. It proves the feasibility of it. There's obviously a lot of work to do here going forward. One area that we're actually doing, which is competing really with this research, is the potential to simply take all the data of the crime in an area and all the architectural information which is already marked up, and simply try to learn the relationship between the environment and the crime already. We couldn't originally do that because obviously we didn't have the data, but now we actually have a lot of information. So we have the data for Manchester, Kirklees, York, all these areas. We have all the crime information. And the councils are also starting to share with us some marked up information. So rather than just getting the images, they're actually showing some information which has some data already in there to allow us to do that. So it's quite an interesting problem, and this whole area of digital policing actually has a lot of opportunities for automated planning, which is quite surprising, something we didn't really realise, and it was interesting for the police to actually approach us to do this prototype. Okay, so that's it. So thank you very much for listening. Thank you. That's all.
Yeah.
Hi.
Hi.
Thank you. Excellent talk, and I really like the application. I have a suggestion. So basically, you took the knowledge of the police officers and you encoded it directly into a planner. And then obviously it got good results based on what the policemen actually thought. There are now models that relate specifically to the design of environments that you can look at, that will maybe able to help you to get generic results that were not thought about by police.
Yes,
For example, if there are like these two driveways that can go into a place, one of them would be the expected one for you to see people. The other one may indicate some criminal intention. So you can change the area in such a way that it will be more appealing to the normal people to go in the right way. And by that you can differentiate early on possible criminal activities from what it's not. And then if you put a model between your application and the planner, you will be able to get more information out of it.
Yeah, no, that's really interesting, and thanks for the advice there. We'll definitely consider it, yeah. It seems like there's a lot to try in this area, to be honest. We're just scratching the surface, really.
This looks like mostly a classification and a feature identification thing so far. Is there a planning aspect to this?
That is manual, is that bit. So the actual, if I just go back to this slide, so the bit about the identification, no, that's manually done. That's not automated in any way. The person is manually marking it. The planning aspect of it is considering the crime that can happen in that environment and trying to plan what can happen.
So are you planning for like an antagonist, like on
exactly. Yeah, you could almost see it as attack planning in a way, where you're looking for the opportunity and then you look to see what can happen. Yeah.
Okay, thank you.
Thank you for the nice talk. I think my question might be related actually to the previous one. So you have shown examples where a pathway could be bad for safety, and also maybe a few trees in the front of a window could also be bad. And I was wondering if these are seen as independent features or there is a relation between them.
Good question, and I'm not too sure I can answer that really. The knowledge we got back from the police was just that is a problem. If you've got the lack of surveillance coming from a property to the environment because of the tree, you know, that's an issue. Whether in isolation, I don't know. That's really one area that we are looking at now. So as I mentioned, we've got a lot of data, a lot of crime data that we didn't have before. We've got specific locations of where crime happened within Manchester over the last 5 years, everything. And it's not just what the crime was, it's, you know, who was involved, what kind of crime it was, what time, etc. And then we've got also the information about the environment, so we can use that to try to work out if there's certain things that are linked, if you like. Yeah.
All right, let's thank the speaker again.
Thank you.
So our second talk is the Clusterdiorite Problem, and it is presented by Sabine Storandt.
I guess everyone is familiar with the traveling salesman problem, which is given a set of n cities and a distance matrix D, which encodes how much time it takes to go from one city to another, so like for all pairs of cities which are there. And the goal is to compute the shortest round tour which visits each city exactly once, right? So everybody knows this, and depending on what the edge costs are, this could, for example, be an optimal round tour. And like most of the algorithms developed for the traveling salesman problem work exactly on this input. But what we forget here, or what is really the input usually to the problem, is some real-world network, some real-world transportation network, most likely a road network, in which we want to do some kind of logistics like this. So what we can observe here is where D usually, so this distance matrix, heavily abstracts from this underlying road network, right? We forget about the spatial positions of the nodes and about the real structure of the road network. We just have this distance matrix. And the main thing I want to get over today, or want to make clear, is that by this abstraction we might lose crucial information which might help us to solve the problem faster. Here's some extreme case, like if all of the points would be located on one shortest path from the one to the other, the problem would be quite easy to solve, right? And so today I want to show you some application where not abstracting to the full level, so like to the full distance matrix, will help to get some easier, faster solution. Okay, so here's the real application we're talking about. It's the dial a bus problem. So I think the name says what the idea is, but let's summarize it quickly anyhow. So usually what you do if there's no public transport available, or if it's like too scarce or anything like that, you call a cab or you call an Uber or something like this, right? So this helps you to get from one place to another, but there are some problems with this. So for example, it's not that eco-friendly if like 100 people at the airport call some Uber and then all go to the city center, because then you kind of induce jams by doing that. And also taxis, it's observed that like 90% of taxi rides are just with a single passenger. And so the idea is to have some collective taxi basically, so have some small bus and hope that people who want to go in the same direction or exactly to the same place can book a seat in this bus instead of using each their own cab or their own Uber. So there's some pros to that, obviously. So it would be cheaper than calling a taxi, maybe not cheaper than Uber, depends. But you would also get this door-to-door service, so you can get picked up everywhere. You can get your delivery location wherever you want. And the idea is, of course, if multiple people share one vehicle, it's more eco-friendly, and you would get better coverage, especially in rural areas, because in rural areas you usually have not so much public transport, but it's also not so easy to get a cab and also not so easy to get somebody driving you by Uber or Lyft from this position to your home place or to your workplace or whatever. There are also some cons. So for example, you have to book in advance at least sometime, so it will be a bit slower than just calling a cab, and it might also be a little bit more expensive than just using the usual bus, which might connect the villages. And there are also some detours. Obviously, if you have door-to-door service, then if there are multiple passengers, you have to also go to their doors, so you induce some detours. And this is where our problem is located. So what we want is to minimize those detours for everyone. So we want to compute optimal bus routes, so optimal routes which really pick up everyone, deliver everyone, but with the smallest induced detour. Okay, so that's a dial-a-bus idea, and there are a lot of pilot projects in many areas this is already available. So we have a project partner who wanted us to do something there. So, and here's the connection to the first slide I showed you, to the traveling salesman problem, because this optimal bus tour planning can be modeled as a variant of the traveling salesman problem. So what is the variant? Well, we have some precedence constraints, because if you want to deliver someone, you have to pick him up first, right? So it doesn't help if you go to his target location if you did not collect him beforehand. So we have these constraints which say, okay, you have to visit this location before the other, and then we want to find the least cost tour which obeys these rules. So for example, this could be some optimal bus tour, and of course the problem is NP hard. Nevertheless, there are some exact algorithms to solve it. One famous one, pretty old, but still one of the best one, is Sarafte's algorithm, which computes the optimal solution in 3 to the power of the number of passengers you want to transport minus 1. So the 3 actually comes from 3 states a passenger could be in, not yet picked up, on the bus, or already delivered, and it's kind of a dynamic program which exploits the search space nicely. But what we can also see here, due to this exponential growth, that already for moderate values of n, this is not really applicable anymore. Okay, so if you have 20 passengers, this is just something you can't run. It gets really huge, so it also uses a lot of space, but also the time will just kill you. Okay. So in the beginning, I told you that sometimes we can use the structure of the underlying road network to get some more information and to make our problem more easable or more easy to track. So this is the idea now. So what we looked at, or where this pilot project of our project partner was aiming at, is rural areas. And at least in Germany, we have seen the same structure again and again. And it's depicted here. And the thing is, what we usually see is like a sequence of villages which are all on the same main road, which connects them to the next bigger town. Okay? And no matter if there is some pickup or target location inside here or not, if you want to go from the left to the bigger city, you always have to cross this village. Okay? So there's no way around. So every going around would be a detour. So you really go basically straight along this main road. And if there are pickups or deliveries in some village, you make these local changes to the tour, but you really have this main thing. Okay. So in classical way to tackle it would be to compute this complete graph of all pairwise distances, and then let's run some algorithm on it, right? So what we propose is, instead of doing that, we have some less abstracted version, which we call the cluster graph. So each village forms some cluster on its own, which is the same as this complete graph we usually would compute on the full instance. But in between, here where this main road is, we just have this one shortcut basically between the villages. So this kind of graph encodes the very same shortest path information as this complete graph, obviously, because we know every shortest path from some location in this village to some location in this village. We'll use this middle part here. So we just need to know the shortest path distances from these nodes inside to the exit point of the village, to the here to the entry point of the next village, and so on, to really have all of the information we need. And this, of course, is less space consuming when computing the full graph, as we see here. So this is quadratic, of course, if you use this one. Here, depending on the size of the number of passengers which want to go to a certain village, this is really like less information to maintain. But what we also will see is that it gives us some idea on how to compute an optimal solution. Okay, so here's the formal problem definition of a Clusterdiorite instance. So we have these clusters, so they are given. So we do not really compute them on our own, but this is a village, and so on. And then we have n passengers, and we use some enumeration scheme to show which passenger wants to go from which location to whichever location. So it induces 2n pickup and delivery locations. And we have 2 additional locations. This is the bus has to go from somewhere and to somewhere in the end. So we have in total 2n plus 2 locations to visit. And for ease of exposition, and also because it's kind of sensible, we assume that the pickups in some cluster, so the bus always goes from left to right, basically. Okay, so we have one bus which like goes towards the city, and another bus which goes from the city back to the villages. We can actually take this constraint away, but then it gets more complicated. So let's stick to that. And the goal is now to compute a minimum cost tour. So we always start at location 0. This is where the bus starts. It's somewhere left here now. And we want to go to location n+1. And like, for example, passenger number 1 wants to go to location 6, passenger 2 to 7, and so on. And now the important thing is what we want to optimize is the edge cost, which is the shortest path distances in the network, multiplied with the number of passengers on the bus at that time. So this means what we want to minimize is the total riding time of all people. You could plug in here different kinds of optimization functions, obviously. Again, we tested some variants of this, but we think this makes sense somehow. Yeah? So you could always, of course, say, OK, you want to minimize the maximum detour somebody takes or something like this, but we now take the global minimization of the total riding times. So what you might think what would happen, or what would always be the case, is that the solution is unidirectional, which means that you would start at the bus starting location, then go to the first village, do all of the pickups and deliveries in there, then leave this village, never enter it again, go to the next village, and so on, right? We call this a unidirectional solution. And the nice thing about this is if there really is a unidirectional tour, or two unidirectional tours can only differ inside the clusters, which means we can compute optimal unidirectional tours easily by just computing optimal solutions inside each cluster and then just concatenating them. Right? So we always have to use the same parts of the main roads exactly once, so we can only differ inside. So this really helps a lot here, because as we've seen, the exact algorithm has an exponential runtime in a number of locations it has to visit. So if you assume that the number of passengers are kind of nicely distributed inside the clusters, this exponent is much smaller here, and we can do it way faster, as we will see in the experiments. But now to some bad news. The optimal tour might not be unidirectional, even in practical instances. We now look at some artificial one. Oh, this is the one cluster. This is the other cluster. And the best unidirectional tour would first look at this cluster only. We'll do something like this. And then it would go over to the second cluster and then do the rest of it. So you don't have to understand the details now, but this would result in a total cost of 49, because we weigh each edge with the number of passengers on board. Bus driver also counts. But the best tour actually would be to first pick up this customer number 1, then deliver him to his target location 4, then go back, pick up number 2, and then go back to the bus depot where also number 2 wants to go. And this would result in a total cost of 47, which is less. But what we see here is also that the definition of a cluster might not be so intuitive, because actually the second cluster is very big, so it has a huge diameter, while the distance between the clusters is very small. And this is also what we will see in practice, where these kinds of instances are hard to tackle, right? Because this is not really a cluster in the sense that we would assume it is. OK, so here we could also, of course, compute this unidirectional cost. Yes. But it's only a heuristic. It's just an approximation. OK, so what we really wanted to look at is whether we can distinguish whether some instance has some unidirectional optimal tour before computing it, so some classifier. And what we did here is we compute this optimal unidirectional tour, and then the hope is to come up with some tight lower bounds. So getting any kind of lower bounds is quite easy, but we want to have some which has at least the potential to be tight. So the lower bound also has to take the number of people on the bus into account, which is not so easy to manage. So we always have to know which is the path and how many people are on it. OK, so the idea is we first distributed the tour cost among the clusters and then came up with lower bounds for each cluster on their own. And now I leave out all of the details because it's quite technical. So the idea for the cost distribution is basically we have these people who go over the cluster, who want to go in the cluster, who want to leave the cluster, and so on. And we count them, and then we distribute the costs of this unidirectional tour. And then we have this lower bound per cluster, and this is where it gets complicated. So the main observation is that any tour which gets across this cluster, so it so this is the first kind of spots it visits, then it leaves the cluster again, when it enters from the other side, it visits those two locations, and so on. And you can interpret all of those as an ordered partitioning of the cluster. So you have all possible ordered partitions of the cluster. And in addition, we have to consider this like from which side we came from, either from the left or from the right, from the entry or the exit. This is what this vector here says. So here, for example, we have the same kind of sets, but here for S2, in this left image, we came from the right and went to the left, and here we came from the right and also exited to the right. So we have all of these possible things to consider. And this gets us a really huge number of possibilities. It's called the Fubini number if you just consider these ordered partitions. And if we also account for whether to enter from the left or the right, we have to multiply it with a factor of 4 here, which gives us already for 6 passengers like 5 million different combinations. So like 8 is the practical limit. We cannot do it for more than 8 people, but 8 people per village is quite a nice number, which is rarely exceeded in practice, at least from the data our project partner had. Okay, so what we do then is to plug this in. So here's the total algorithm. So it's actually 3 algorithms in one. So if we do the full thing, so we first compute the unidirectional solution, then we go cluster by cluster, compute a lower bound, and if at some point the lower bound for the cluster does not match the cost of the cluster, we just compute this expensive optimal tour cost, and if we don't find a violator, we return this unidirectional solution. And so if we just leave out this part in the middle completely, we just have some heuristic. But the good thing is if we just leave out that line here, so just the exact computation, we also have some heuristic, but we also have some instant-based approximation guarantee. So we always get some lower bound, which means we can have at least a certificate how good our solution is in the end. So some experiments. So we did experiments on artificial and real-world benchmarks. Artificial means we just put a line in the plane and then put squares on it and threw locations inside. And for real-world instances, we had real bus routes and then had some random pickup and delivery locations inside. Okay, so results. On artificial instances, we see here Saraftis does not really scale well. So for more than 12 passengers, we could not really compute it in a reasonable amount of time. And we see this is unidirectional solution. It comes basically for free. And the classification algorithm is also way faster than Saraftis, and this effect is more pronounced the more passengers you add, obviously. And what's important here to see in this left image is that really a huge amount of these problems has a unidirectional solution. So everything which is green here, so like if there are 16 kilometers between villages, basically everything is unidirectional. If you get the villages closer and closer, the number decreases. But we still see, even if they are pretty close, 50% of instances have this unidirectional tour. And we see here the recalls are the percentage of the unidirectional things we find. And we see it also rises, of course, with the distance between the villages. Okay, and on real-world instances, we see some, basically the same effect. If they're really close together, it's hard to classify. If they are far apart, it's very easy, and we get a good recall. And if you just use it as a heuristic, we can show via our lower bounds that the unidirectional tour is really good approximation of the best optimal tour. Okay, so yeah. And what we also observed, if we don't find a tight lower bound, it's usually very, very close to the cost of the unidirectional solution. So very small improvements in the lower bound construction could give really the recall a big boost. Okay, so yeah, summary, over 70% of our tested instances exhibit a unidirectional optimal tour, so it makes sense to look for one and to certify that this is really optimal. For up to 7 passengers, our approach is really fast, and the combinatorial explosion kicks in. Okay, so main message, as I told you from the beginning, is not abstracting too much from the transportation network might pay off in such traveling salesman problem instances. And there are lots of ways to improve it, like finding better ways to cluster the instances, not just using the villages which are there, but really considering the distances and so on. And here's a cake encoding the problem. Thank you.
Questions?
Thank you for the great talk. I was wondering if for the future work, if you would consider also like how fast is to travel some path, because I live in the UK and sometimes the roads are so tiny to go anything better than 5 miles.
Yeah, so actually, the places it was tested is more or less like really rural areas, so there's not too much traffic going on anyway. So this was not a big problem, but then the closer we get to the city, there are of course jams appearing. So it might make sense to make it time dependent, but then it's really like if we cannot really look ahead what the road conditions will be, then getting some lower bound might not make too much sense. So maybe we should go for some optimal solution first and then see how to adapt it in real time if something changes. But we will need perfect prediction to get a tight lower bound. So I think this is not easily possible.
Thank you. I just wanted to confirm, are you solving a TSP with pickup and deliveries?
Yes.
And so have you looked at the OR literature, or the optimization literature, because there's of course been many works on this, and why did they not apply to your context?
So we looked at, so actually you can substitute Sarafta's algorithm for any kind of algorithm you like, and it will work just in the same way. So if you can solve smaller instances inside the clusters, and then you can use some algorithm to solve the overall problem. So what was really important for us is to solve it optimally. So there are a lot of heuristics, obviously, and also approximation algorithms, but we think with every kilometer saved, driving time for everyone, it gets more attractive to use this kind of transportation mode. So it's really worth going for the optimal solution.
I may have a suggestion to use decision diagrams, multivariate decision diagrams, to represent all paths within a cluster.
Okay.
You have a combinatorial explosion, but you don't have to explicitly list all of them one by one. There's lots of symmetries typically.
Yeah, that's true.
And on the scale of instances that you're considering, n equals 12, for example, I think this could work very well. If I'm not mistaken, there's a presentation this afternoon on using decision diagrams for similar problems, so maybe that could interest you.
Yeah, that might make a lot of sense. So it's just really wasteful the way we compute these ordered partitions. It's not only this what I showed you, but there's also a 4-step procedure to then actually compute the cost, and there's a lot of redundancy in there which we did not exploit, so this might really make a lot of sense, yes. Thanks.
Okay, so let's thank the speaker again. So the next talk is mixed integer programming versus evolutionary computation for optimizing a hard real-world staff assignment problem. And the presenter is Martin Krejca.
Whatever. So thank you very much for sticking around, and thank you for the nice introduction. Actually, so now let me be honest, I have no clue what scheduling and planning really is about or so, and we just saw 2 nice talks with a lot of insights, intelligent information going on. We don't know anything about this, so we're quite dumb and we just did stupid stuff. So this is what this evolutionary computation is about. So my background is I'm a theoretician. I'm doing research in the environment of evolutionary algorithms. And so this basically is more of a pitch kind of for saying why these algorithms are cool. And the title should actually more be, okay, evolutionary algorithm bet a mixed integer programming approach for one real world problem. And I'm going to talk about the problem in a moment, but you may have also noticed that there's quite a lengthy list of authors, and this is because this has been done in collaboration with a lot of undergraduate students, so which I want to show here. So these are basically the students that worked on this project for roughly about a year. So basically credits all due to theirs, and I'm just going to present the results here. So now let's move on. So the idea, so what is the domain of our problem? So we were approached by an industrial partner in the professional services domain, and there are 4 major players actually, mainly known, as far as I know, for tax audits. So you have these 4 basically companies, and they have tons of different employees with different skill sets and that they want to kind of assign to certain jobs. We were actually approached by KPMG, and they have the following, I would say, classical scheduling task that we were kind of faced to solve. So we have here a picture of a schedule, which is also part of a tool that the students develop. And when I say classical, it's basically as easy as you can imagine. So we just have some employees, so every row basically just denotes an employee. We have some days or weeks, so chunked in this up. And the different colors are just what they call different engagements. So basically different jobs where we want to assign the employees to. And in the end, we just want to have one schedule for this. So, and for all of the employees for the amount of a single year in advance, basically. And this has been done up to date manually by managers. I'm not sure how they did it actually, but I guess they have to get their salary one way or the other. So, and I mean, this now may look very easy, but of course there are far more harder things to consider. So there are some hard constraints which I'm not going to talk about, but we have different objectives which we kind of had to get through the hard way by just talking back and forth with the manager over a course of months. So that was kind of complicated, but we ended up with the following objectives. So in no particular order, really. The first one says, okay, assign employees according to their skill levels to engagements. I shouldn't get too close there. So something that you do not see here, so this is all kind of not in this view, but a huge part of the problem, as I said before, is that the employees have different skill sets, of course, and the engagements, of course, also ask for different skill sets. So we kind of want to manage to assign good employees according to their skills to kind of good engagements. And of course, the employees can also have skills in varying levels, and the assignments may ask for skills of varying levels. So we kind of want to have a good fit going on there. Another thing is, okay, so the employees should work on similar engagements as last year. This just basically is what KPMG wants, so kind of that the employees know the project partner they're working with and the project partner knows the employees, so everyone can work just better because they've known one another for quite some time. Kind of straightforward. Okay, as few employees per engagement as possible. That also makes kind of sense. You don't want to overload a customer basically by just throwing tons of different employees at them, but just having a few contact people basically they can talk with. It's also fine. Now the next one, okay, employees should work consecutively. So if you've seen that here, we have a lot of colors of same color in a row, basically. Now this may look like it's nothing or just a minor detail, but this basically is one of the most important points they pointed out to us. So like the most heavy objective, I would say, because they want that the employees, while working for a certain customer or so, are there consecutive number of days, so that they kind of get the task done in one row, so to say, and that the customer is also familiar with the employee they're working with and that there are no breaks in between, which makes it look like, okay, it's a trivial thing to do, but this basically is the kicker. So this was the hardest one in the problem, which makes the problem tremendously hard. Doesn't look like it in the first place maybe, but this is really the toughest of these objectives. Well, the other one is minimize travel distance. Of course, the employees have to go to certain locations while doing so. We want to minimize the overall travel distance. The one is not so important. Okay, so the working hours of employees should be fully utilized, of course. So while you're there, you just want to make sure that you work all of the time available to you to get the job done as quickly as possible. But while doing so, you of course also want to minimize the overtime working hours, which I'm not sure if anyone of you is familiar with this. But they have some seasons where they're basically always working overtime. So you kind of want to make sure that they can also cut some slack or so. So also somewhat important. Okay, so we have all of these objectives basically that also go into the regular scheduling we see behind me. And now, as I said, like we have no clue about scheduling at all. So we just use a brain dead approach basically, which is called evolutionary algorithms. And I just want to kind of show you the rough idea of how this works, so the basic template. Oh yeah, what I have said before, so the managers have done this before manually. I don't know how or whatever, it's not my problem. So when talking about evolutionary algorithms, so they're randomized search heuristics, so since we're having an optimization problem here, they kind of apply. And the general idea is we just have a bunch of what we call individuals, which are basically just some solutions. So in our context, all of these are just some schedules we're having here. And now what we're doing, since we have no clue what we want to do in the first place, we just take some of the solutions and vary them, right? So we apply some sort of variation operator and create new solutions. Usually this is done by just taking a single solution and perturbing it sort of locally. However, this is not to be confused with a local search, because the idea of evolutionary algorithms is to apply some random changes that usually in expectation only make kind of a local change to the solution, but they have the potential of changing the solution like in a global way or in a more drastic way. If you use these kind of variation operators, usually known as mutations, so just changing single solutions on a kind of local basis with the potential of kind of global impact. Okay, and so far, I mean, we didn't do anything clever at all. We just created some new solutions by just guessing randomly. Okay, so we kind of want to get the objective in there, and that's what we do with the next step. by just selecting some individuals. Of course, there are many different ways of how this could be done. So this little f just should denote that this is where our objective function comes into play, funneling down this set of solutions. What we did is just a common elitist way where we just rank all of the solutions by their quality and take a certain subset of the best solutions and then hope that we kind of get a direction of where this leads to. And that's basically it. And then we iterate it, right? We cross our fingers that we eventually end up with good solutions. And that's it, right? So as I said before, these are just some heuristic approaches, so we do not know whether we'll end up with an optimal solution or not, but we don't really care whether we do or not, right? We're just interested in some good solutions. Okay, so this is the general framework that we used for the problem. Now there was like one little trick that we also used, which is something that you usually should do. So you should only apply these algorithms if you don't know what you should do, right? And I mean, I said, we didn't know what we wanted to do, so this is why we went with this approach. However, there's a sub-problem inside of this scheduling problem that we can solve optimally. So of course, if you can do something like that, you should do it. So we ended up with a two-stage approach, basically. And the first phase was we only used the evolutionary algorithm to kind of assign these employees to a certain engagements and certain days. And that's it. And if you recall, the objective says, okay, we also have to do the skill matching and all of this. And this is something that the evolutionary algorithm does not do, because we can actually have a min cost max flow going on for that kind of models, okay, the working hours as the flow that we want to get to the goal, basically. So we can solve this sub-problem basically optimally, so we do not put it inside of the evolutionary algorithm. What we don't know what to do is how the scheduling is actually done. So this is where this guessing random part comes into play. Now I just want to quickly also give you an overview about the mutation operators we use, kind of how to perturb certain solutions in order to get new solutions. And they're actually super simple. So, I mean, what would you do? Okay, you may want to add like an employee. So assume you have some free slots here. And all we do is just we pick one employee that would fit into the time slot, just place it there, and then with a decreasing probability, add it for the following day and so on, right? So because I said it's very important that we have this consecutive number of the same employee working on a project, so this kind of gets this monochromatic rows, or the columns rows, this fashion. Now, of course, another mutation operator is that we kind of want to remove an employee. If we have someone there and they may not fit or so, we want to remove them, we do the same thing. So with decreasing probability, basically, we just remove them. And now for the last, for this monochromatic rows, we have another mutation operator that says, okay, if we have these different colored, so this is just one employee basically on a project, but with different colors, this is something we do not like. So we just color all of them the same color, like with the majority, for example, here, but it doesn't really matter, just so that we get these monochromatic rows, so to say. And then we also have like a random number of operators perturbing the solution, and that's basically it. So this is all that the algorithm does, the evolutionary algorithm. And yeah, that's all the magic that's behind that. And as I said in the beginning, that basically works. And it's very easy with this approach to kind of get better solutions than the managers did manually, okay, but I mean, that was to be expected. So we kind of tried out a different approach, which is more straightforward, I think, or something that at least comes to mind pretty quickly, which is, of course, to model this problem as a mixed integer linear program. And I don't know what kind of solver you would suggest for this situation, but I mean, of course, like what comes to mind, I guess, is Gurobi. Because, I mean, as it says on the website, it's the fastest solver. And by no means, I don't want to bash Gurobi in this talk, because, I mean, Gurobi is great. It works for many different problems. It goes for optimal solutions, and it also provides you like a kind of bounds on the optimal solution, telling you how far away from an optimal solution the current solution is or so it gives you some guarantees. So Gurobi is a great tool, definitely should give it a try. Nonetheless, for our problem, it didn't really work out. Right? So this is basically what this talk is about. So now for modeling our problem as a MIP, we of course have like different variables that go into play, just to give you some idea. So we have 920,000 continuous variables. Okay, not a big deal. then we have 450,000 discrete variables, right? So this is a hugely discrete problem because we want to have certain employees on certain days, also with certain skill sets, and all of this is discrete. So kind of, this is where the problem basically lies, I would say, all of these discrete variables. And then, of course, we have some constraints, which are these 30,000 constraints, roughly. And now one thing I didn't mention before, but of course, if we want to model this as a MIP, is that our objective function needs to be linear, right? I mean, you can also allow for certain quadratic parts or so, but basically, the objective function should be linear. For the evolutionary algorithm, it does not have to be linear. It can be anything that just tells us how good a solution is. But for the sake of comparison, we went with a linear objective function. In the end, for our project partner, we did not go with a linear function, but with a more contrived function, but whatever. So what we see now here basically is just the results of this linear function. And we just compared the results against one another. So here are the results now for this, so the A versus Gurobi. And now what you'll see is we first let Gurobi run, of course, to kind of get an idea of how good it could get. We let it run for roughly a week or so. And after 100 hours, so roughly 4 days, it came up with a solution that it could not improve upon for the rest of the week or so, basically. And then we just let the evolutionary algorithm run different time budgets. And we just saw, just did this for 210 times, and then we just measured how often we bet Gurobi in this time interval. So here you see the number of hours we let each evolutionary algorithm run. I mean, since it's a random algorithm, it kind of makes sense to restart it because there may be some variance in the play. And here's the percentage of runs that bet Gurobi. So as you can see, pretty early on, it already beats Gurobi. But I mean, the percentage of algorithms doing so is very small. Whereas if we invest like 5 hours, it's at roughly 45%. Okay, that's quite cool. But what's actually the kicker here, I would say, is that we have an almost linear trend here, which is nice if we want to parallelize stuff, because now, roughly speaking, instead of just letting one algorithm run for 5 hours, we can let 5 algorithms run, each for 1 hour in parallel. We would roughly get the same percentage of success. Not exactly, but roughly the same. I mean, the math turns out to not be that straightforward, but basically the same thing. So this is something that we also tried out, in what we'll see in the next plot is where we just have a certain time budget, and then we let that many algorithms run in parallel such that we get to an overall time budget of 100 hours, which is the same time budget that Gurobi kind of used to get to its best solution it found so far. And this results in this plot, right? So this means each of the evolutionary algorithms had 5 hours, which would mean 20 algorithms to get to a time budget of 100 hours. So here 6 minutes is where they start beating or getting to a solution that has the same quality as that of Gurobi. This would, I think, like 1,000 algorithms or so in parallel, so no one would do that in the first place, but it just theoretically speaking. And as you can see, okay, so the more time you allot to your algorithms, of course, the better the solution becomes, and it just keeps increasing from there, right? So what we see here is the gap value. So as I said before, Gurobi gives you like an upper bound on the quality of how good a solution can be. And the solution Gurobi came up with is like at 10.5% roughly or so within this 100 hours. And now our algorithms just keep increasing or decreasing the gap value, basically increasing the quality of the solution. Whereas like 4.2 hours roughly, they're within 2% gap or 1.7% gap of an upper bound, an optimal solution, right? So maybe even closer to a real optimal solution for the problem. And this is something that I have to say we actually did not think of would be possible. So when we first started out the project, we gave the students 2 different tasks that, okay, some of you can try out this evolutionary algorithm, some of you can try out Gurobi. We're pretty sure Gurobi will win, but I mean, just give it a try. And this is the result of it. So we were surprised by that. I mean, maybe you too. And that's all I wanted to tell you. So thank you very much.
Questions?
Thank you for your presentation. I'm also quite surprised actually by your findings. In particular, the model is huge for mixed integer linear programming standards, 1.5 million or almost 2 million variables in total, and an enormous amount of integer variables. So what I find most surprising is that Gurobi can even parse Gurobi is a black box generic MIP solver, and it can parse that problem and actually get an extremely tight lower bound, because you have a 2% or even less optimality gap at the end, which is surprising, especially with 450,000 binary integer variables. So I think that's great news for Gurobi. That's just the first thing I wanted to say. That's surprising to me. Of course, you did great work getting your solutions to that 2% interval. That's very well done. My question actually is, did you run Gurobi on the full problem, including this min cost flow part, the entire problem, or only on the first part where you generate the schedules?
So the modeling with Gurobi is on the full problem, so we did not have this two-stage approach. However, we asked some experts or so that also work with Gurobi, and they told us Gurobi should be able to figure out such sub-problems and also solve it by itself, basically automatically. So we did not have this two-stage approach. We just thought, okay, we don't know what Gurobi basically does, so we don't want to fiddle with it too much. We just give it the instance as a whole and should work with it by itself, basically. So this was only done for the evolutionary algorithm, because this is something where we know how to approach it, what we can do, how to fiddle around with.
Thanks. If I may, one follow-up question. Did you consider constraint programming or a combination? For example, the skip solver has constrained integer programming where you have both, say, scheduling constructs for activities and resources, and in addition also the integer programming part.
Yeah, we were thinking about it, but in the end we only had limited time, and the students had to, they didn't know about anything of that. They had to basically go for one approach, so we went with Gurobi because it's to us the most common solver. Also, I don't know what the benefits of CSP would be over Gurobi with respect to that, but maybe we can talk offline or so, if there would be some advancements or some other cool tricks to use for that, but we did not go for any other solutions, basically.
Sure. Thanks.
So let's thank the speaker again.